The three interdependent factors in achieving a gasoline engine's full operating capacity are proper air-fuel mixture, proper compression, good combustion. The role of maintaining the proper air-fuel ratio is played by the fuel system. The two types of fuel systems are the traditional carburetor, which operates mechanically, and the electronic fuel injection system, or EFI, which uses a small computer to obtain the proper air-fuel ratio. Now let's look at the construction and operation of the carburetor. In this video, we will introduce the following 4 points. First, the components of the fuel system. Second, the principle of the carburetor operation and the importance of a proper air-fuel ratio. Third, the construction and function of the carburetor. And finally, the adjustment of the idle mixture. The fuel system is made up of the following components. The fuel tank, where the fuel is stored. The fuel filter for removing impurities. The fuel pump, which sends fuel under pressure to the carburetor. The carburetor, where air and fuel are mixed, atomized, and sent to the engine. The charcoal canister, which prevents gasoline vapors from escaping from the fuel tank. And the fuel lines, which connect the various components. The fuel inlet line and the fuel sender gauge are installed in the fuel tank. The fuel filter contains a filtering element to remove water and foreign matter from the fuel before it enters the engine. The fuel pump draws out fuel from the fuel tank and sends it under pressure to the carburetor. The diaphragm-type fuel pump shown here is the most common type of fuel pump used with carburetors. The diaphragm-type fuel pump of the 4AF engine is installed on the engine block and is driven by a cam on the engine's camshaft. The fuel pump has a diaphragm in it and a pair of valves which act in the opposite direction from each other. These valves are actuated by the reciprocating movement of the diaphragm and feed the fuel to the carburetor. The charcoal canister prevents the fuel vapor from escaping from the fuel tank. The canister is filled with activated charcoal. The vapor that passes through the charcoal is absorbed and combined with outside air, then sent to the combustion chamber where it is burned. The carburetor mixes the proper amount of air and fuel in accordance with the operating conditions of the engine and sends it to the combustion chamber. The principle behind this is similar to that of a manual paint sprayer. When air is blown through the pipe, the liquid inside is drawn up and mixed with the air, forming a spray. An increase in the speed of the air blown through the tube will create to draw up the liquid and create a mist. This is a model used to demonstrate the principle behind the carburetor. Air is blown in at the bottom, creating a vacuum which forces the liquid out. We will explain the functions of the carburetor using this model. First, we will conduct a test in which the nozzle of the fuel pipe alone protrudes into the air tube. If a vacuum is applied to the bottom of the tube, we see that the fuel rises in the pipe a little, but due to insufficient air pressure, enough fuel will not exit the pipe. Now, let's narrow down the mouth of the tube to speed up the airflow and see what happens when we try it again. As you can see, liquid is atomized. that is, changed into a mist that can be blown out through the pipe. This is basically how a carburetor works. The portion that was made narrower to speed up the airflow is called the venturi. Below the venturi is a throttle valve which controls the air-fuel mixture. It is connected to the accelerator pedal. These comprise the fundamentals of the carburetor. This is how the air and fuel are mixed, but it leaves us with one problem, namely how to achieve and maintain the proper mixture of air and fuel, or the correct air-fuel ratio. Theoretically, the optimum ratio for combustion is 14.7 parts of air for every 1 part fuel. If this theoretical ratio is achieved, the result will be easy engine starting and complete combustion. As long as a mixture at this ratio is supplied by the carburetor, the engine will run smoothly. Now let different driving conditions beginning from when the vehicle is started. Naturally, the engine is cold, making it harder for the fuel to be atomized. This alone is enough to create an improper air-fuel mixture. Hence, it is necessary to provide a greater ratio of fuel to air. Just when the vehicle is accelerating, we know that fuel is heavier than air. So since the amount of air is increased when the accelerator pedal is pressed, the amount of fuel also must be increased to obtain sudden acceleration. When the engine is idling, or when the vehicle is traveling at low speeds, fuel and air do not mix well. Because of this, it is necessary to achieve the theoretical ratio, or a slightly richer mixture. A greater ratio of fuel to air is necessary to obtain the needed power when climbing hills or other times when the throttle valve is wide. The theoretical air-fuel ratio or a slightly leaner mixture is needed when driving on straight even roads at constant speeds. So as you can see, the carburetor must create the proper air-fuel mixture under a variety of driving conditions. Although there are many types of carburetors, we will examine the workings of the carburetor used for the 4AF engine. This carburetor is called the double barrel type because it has 2 passageways, or barrels, for carrying the air-fuel mixture. This is the primary barrel, and this is the secondary one. The air that passes through the air cleaner enters the barrels here. The fuel from the fuel pump enters the float chamber here. Next, let's look at the float system. The venturi determines the amount of fuel that is drawn in and mixed with the air. However, if there is any variation in the height of the nozzle from the fuel surface, labeled H in the diagram, there will be instability in the air-fuel mixture. So, the float system was devised to maintain a stable level of fuel in the float chamber, which changes in the distance between the nozzle and the surface of the fuel. The float system consists of the float chamber, the float, and the needle valve. The air vent tube ensures that a uniform pressure is maintained in the float chamber and above the choke valve at all times. If the fuel level drops, the float will also drop, causing the needle valve to open and allow more fuel to enter the chamber. Conversely, if the level of fuel increases inside the chamber, the float will rise and close the needle valve, stopping the flow of fuel. The 4AF engine carburetor is provided with the variator to maintain the proper air-fuel mixture. Of these, only the primary barrel is used when the vehicle is traveling at low or medium speeds. Both the primary and secondary barrels are utilized. Let's look at these in order. The primary low-speed circuit supplies the air-fuel mixture when the vehicle is idling or traveling at low speeds. Here we will use a model to demonstrate. As you can see, the throttle valve opening is very small when the vehicle is idling or traveling at low speed. The amount of air allowed in by the Venturi is small, insufficient to draw up much fuel. Now let's place another port below the Venturi and see what happens. Because the vacuum below the Venturi is greater, more fuel is drawn into the barrel. This is the primary low-speed circuit. The actual flow of the fuel is as follows. It leaves the float chamber and passes through the main jet, then through the slow jet, which controls its volume. It then goes to the primary air bleeder, where it is mixed with air, and then to the economizer jet, where the volume is further controlled. Then the air from the primary air bleeder is mixed well with the fuel and delivered from the idle port. The idle port is supplied with an idle mixture adjusting screw to allow the idle air-fuel ratio to be adjusted. The mixture can be made richer while the engine is idling. When the throttle valve is opened slightly from the idle position, there will be an increase in airflow. However, the fuel supplied by the idle port alone would result in a lean mixture. To prevent this, there is another port called the slow port. The effective surface area of the slow port increases as the throttle valve opens. This prevents the mixture from becoming too lean until fuel can be delivered from the main nozzle. The fuel supply and slow port stops when the throttle valve opens to draw out fuel from the main nozzle. In the primary low-speed circuit, there is a fuel cutoff solenoid. When the ignition switch is off, the root is closed and the fuel supply is interrupted. In some engines, a fuel cutoff solenoid also activates when the engine is running at slow speeds. Next is the primary high-speed circuit. The construction of this is similar to that in the carburetor model we looked at earlier. It is the most widely used main circuit, although there are mechanisms to activate to assist when extra or speed is needed. This side is the primary barrel on this model. The Venturi is designed this way for maximum mixing of air and fuel. The primary high-speed circuit works as follows. When the throttle valve is opened wide, allowing for a higher speed and volume of air to Venturi, the amount of fuel that is delivered is equivalent to the intake air volume drawn into the barrel. The amount of fuel is controlled at the main jet before it is mixed with the primary air bleeder and injected from the main nozzle. The fuel is atomized by the air flowing at high speed past the Venturi, from which it enters the combustion. This is how the air-fuel mixture is regulated during idling at low and medium speeds. However, this alone will not produce the power needed during high-speed operation. This is why the double-barrel carburetor has a secondary barrel. The construction of the secondary barrel is the same as that of the primary barrel. It has a high-speed circuit, which is its main circuit, and a low-speed circuit which prevents the mixture from becoming too lean when the throttle valve opening on the secondary side is small. Let's look at the secondary low-speed circuit for the secondary barrel. If the primary throttle valve opens more than 60 degrees, the cam in the kick-up system will force the secondary throttle valve to open slightly. Is then secondary slow port, causing fuel to be delivered to the intake manifold. When this happens,
The vacuum bleeder, which is part of the venturi, produces a vacuum which opens the secondary throttle valve. When the engine RPM rises, the pressure from the vacuum bleeder overcomes the diaphragm spring, which in turn causes the secondary throttle to slowly open. The secondary low-speed circuit, like the primary low-speed circuit, uses a solenoid, so that when the ignition switch is off, the root is closed off. Now let's move on to the secondary high-speed circuit. When the secondary throttle valve starts to open, a vacuum is created by the vacuum bleeder. This is strengthened by the diaphragm, which causes the second throttle valve to open further. The fuel is injected from the secondary main nozzle. In this way, both the primary and secondary barrels work together to produce the air-fuel mixture necessary for high power. Now let's take a look at the power circuit. The high-speed function provides insufficient fuel when climbing steep grades or when extra. This power circuit comes into the picture. The power circuit consists of a power valve set into the root that communicates with the primary main jet. It opens to allow more fuel to flow through to provide the rich mixture needed when extra power is called for. When driving at a constant speed with the opening of the throttle valve small, the power valve is closed due to the high manifold pressure. When a big increase in power is needed, the driver depresses the accelerator pedal, thus opening the throttle valve wide. This causes a decrease in the manifold pressure. When the pressure in the manifold falls below the standard value, the spring pushes down the power piston and opens the power valve. The flow of fuel becomes less restricted, and the fuel is delivered from the main nozzle. Now let's take a look at the acceleration pump. We all know that to achieve quick acceleration, the driver needs to depress the accelerator pedal suddenly. The acceleration circuit is designed to prevent engine hesitation during such sudden acceleration. With the pump-type power circuit, when the throttle valve is suddenly opened, the pump lever depresses the pump plunger. This increases the flow of fuel from the acceleration pump jet. Slowly releasing the accelerator pedal allows the pump plunger to rise to the usual position. This causes the fuel to be drawn up into the pump chamber, where it is held in reserve for the next time sudden acceleration is needed. There is also an auxiliary acceleration pump that assists the acceleration circuit when the engine is cold. When the engine coolant at a low temperature and the TVSV is open, the pressure from the intake manifold causes the diaphragm of the power assist pump to activate and fill the pump with fuel. If sudden acceleration is attempted at this point, since the pressure in the intake manifold falls, the diaphragm spring causes the fuel pump to be sprayed out of the nozzle. In this way, the pump makes up for the lack of power in the main speed pump. This brings us to the choke system. Without a choke, it would be difficult to start the engine in cold weather. The choke valve is provided above the nozzle to decrease the amount of intake air during starting. In this way, the choke helps start the engine and improves drivability. The choke valve is located in the primary side air horn. At present, as is shown here, the most common type is the automatic choke system. We will also introduce the electric automatic choke, which is currently in use in most vehicles. The automatic choke is controlled by the contraction and expansion of a bimetal element.
When the temperature falls below a set level, depressing and releasing the accelerator pedal will cause the choke to be completely closed by the contraction of the bimetal element. After the engine is started, current will flow through the electronic coil. This will generate heat, which will cause the bimetal element to expand and open the choke either slightly or all the way. Here we have the fast idle mechanism, which raises the engine idle speed when the temperature is cold in order to maintain proper engine operation. When starting the engine in cold weather, depressing the accelerator pedal once and then releasing it will cause the fast idle cam, which is connected to the choke valve by a rod, to open the throttle valve slightly. In this way, a slightly higher engine idle speed is achieved. After the engine is warmed up, it will continue to run at a fast idle, even if the choke valve opens, until the accelerator pedal is depressed again. When this happens, the cam follower rides up over the cam and the fast idle is released. This causes the throttle valve to return to the normal idle position and the engine speed to drop. Let's move on now to the unloader mechanism. The unloader prevents the air-fuel mixture from becoming too rich if the engine is started and runs cold without sufficient time given for warming it up. When the accelerator pedal is fully depressed, the throttle shaft arm moves the fast idle cam to force open the choke valve slightly. This allows more air to enter to prevent the mixture from becoming too rich. Let's look at the choke breaker. During cold starts, the choke valve may remain closed, providing an overly rich mixture, which could lead to engine stalling. The choke breaker causes the choke valve to open slightly in this situation to prevent the engine from stalling. When the engine is started, the low intake manifold pressure causes diaphragm A to slightly open the choke valve. Till the engine warms up and the coolant temperature rises to normal operating temperature, the TVSV opens, and the vacuum from the intake manifold causes the choke opener diaphragm B to open. After this, the choke valve is operated by the auto choke mechanism. Now, let's see how to adjust the idle speed and mixture. You should use a CO meter to do this if possible. First, in order to adjust the speed mixture properly, we must make sure that the following conditions are met. Make sure that all the electrical accessories are turned off. Check to see that the transmission is in neutral. Make sure that the engine is warmed up. Confirm that the ignition ting is set properly. Examine the float level in the carburetor to see if it indicates the correct fuel level. And finally, check to confirm that the choke valve is completely open. After these conditions have all been fulfilled, connect the engine tester and proceed to check the idle speed. Remember that the test must be done with the air cleaner in place. In some models with an air suction system, you move the air suction vacuum hose and plug it with a hose plug. Turn the idle mixture adjusting screw to raise the engine RPM to its highest permissible idle setting. Then turn the idle speed adjusting screw to set the idle to specify idle mix speed. Repeat these 2 steps until the engine RPM will no longer go above the highest permissible idle setting. Finally, turn the idle speed adjusting screw to set the idle speed to the specified setting. After this, rev the engine to about 2,000 RPMs for 30 to 60 seconds. Give the idle speed 1 to 3 minutes to stabilize, then test the exhaust by inserting the CO meter probe 3 centimeters or about 16 inches into the tailpipe. If the CO emissions are above standard, or if the engine is still running rough, repeat the previous steps and adjust the CO emissions with the idle mixture adjusting screw, as well as adjusting the idle speed with the idle speed adjusting screw. Next, we will see how to adjust these without the use of a CO meter. In model with an air suction hose to the air cleaner, remove it and plug the end with a hose plug. Turn the idle mixture adjusting screw to raise the engine RPM to its highest permissible idle setting. Then, turn the idle speed adjusting screw to set the idle to the specified idle mixture speed. Repeat these 2 steps until the engine RPM no longer go above the highest permissible idle setting. Finally, turn the idle mixture adjusting screw to set the idle speed to the specified setting. In this video, we have discussed the fuel system by focusing on the design and operation of the carburetor. The fuel system greatly affects the vehicle's operation, power output, and fuel efficiency. It is our sincere wish that this video, in connection with other training materials, will help you to understand the fuel system and be useful in your daily service operations.